Hey everyone, welcome to today's explainer. I am so thrilled to have you here. If you've ever found yourself a little tangled up by the concepts of motion, vectors, or gravity, well, you are in exactly the right place. Today we're going to dismantle some of the most common physics misconceptions by tackling 9 essential questions in strict numerical order. We're going to break down these concepts so they actually stick. So get focused, get ready, and let's unravel the physics of motion together.
Question 1. Is it possible that displacement is 0, but not the distance? Under what condition will displacement be equal to distance? Take just a split second to ponder the physical difference between the total ground you cover and where you actually end up relative to where you started.
Well, the answer is a big yes. Displacement can absolutely be 0, while distance isn't. Think about a student who walks 10 meters east and then turns right around and walks 10 meters west, back to their starting point. The total distance they walked is 20 meters, but their displacement, which is just their net change in position, is strictly 0, because they're right back at square one. Now on the flip side, displacement equals distance when an object moves in a straight line in one direction without ever changing direction. If that same student just walks 20 meters straight east without turning back, both the distance and the displacement are exactly 20 meters. Question 1. Complete lit.
Moving right along, question 2. Does a speedometer measure a car's speed or velocity? It's an instrument we look at on our dashboards every single day, right? But scientifically speaking, what is it actually telling us?
So, a speedometer measures the speed of a car, not its velocity. See, speed just tells us how fast an object is moving. It's what we call a magnitude. Velocity, however, tells us both the magnitude of motion and its direction. A regular dashboard speedometer only gives you that magnitude. If it reads 60 kilometers per hour, it tells you exactly how fast you're moving, but there is no way to know whether you're heading north, south, east, or west. You would literally need a compass combined with that speedometer to know your actual velocity. Question 2.
All right,
complete.
here is question 3. Is it possible for an object to be accelerating and at rest at the same time? Explain with an example. I know, accelerating and at rest at the exact same time, it sounds like a total contradiction, doesn't it?
But the answer is actually yes. Instantaneously, an object can have 0 velocity while still having a non-zero acceleration. It's all about split-second timing. Imagine a ball thrown straight up into the air. As it goes up, it slows down until it reaches its absolute highest point. At that exact microsecond at the peak, its instantaneous velocity is 0 meters per second. It is technically at rest for that instant. But gravity never takes a break. It is still pulling downward at approximately 9.8 meters per second squared, and that is exactly what causes the ball to immediately start falling back down. Question 3 complete.
Let's flip it around for question 4. Can an object have 0 acceleration and non-zero velocity at the same time? Give an example. Think about a scenario where you're moving, perhaps in a car, but everything is perfectly steady.
Again, the answer is yes. You can absolutely have 0 acceleration and a non-zero constant velocity, as long as you're moving with a constant velocity in a straight line. If you are cruising down a perfectly flat, straight road, maintaining a steady 20 meters per second heading east, your acceleration is strictly 0. Because acceleration is defined as a change in velocity, and neither your speed of 20 meters per second nor your eastward direction is changing, your acceleration is exactly 0 meters per second squared. Question 4, complete.
Question 5. A person standing on the roof of a building throws a rubber ball down with a velocity of 8.0 meters per second. What is the acceleration, including both magnitude and direction of the ball? Keep that initial downward throw in mind. It's a bit of a trick.
Okay, so here's the crucial point. That initial throw does not change the laws of physics. The ball's acceleration is approximately 9.8 meters per second squared downward. That initial velocity of 8.0 meters per second just means it starts off moving pretty fast. But the second it leaves the person's hand, assuming we ignore air resistance, the only force acting on it is gravity. And gravity pulls downward at a constant acceleration of 9.8 meters per second squared for all objects in freefall. The force of the throw doesn't change gravity's pull one bit.
Question 5. Describe a situation in which the speed of an object is constant while the velocity is not. This is a classic puzzle to see if we really grasp the difference between scalar and vector quantities. The absolute best example of this is a car driving around a circular track. Remember, velocity includes both speed and direction. If the car's speedometer stays glued at 20 meters per second, its speed is totally constant. But because the track is a circle, the car's physical direction of travel is continuously changing at every single point along that curve. Since the direction is changing, the velocity has to be changing. So constant speed definitely does not mean constant velocity when you're turning. Question 6, complete.
Okay, question 7. Can an object have a northward velocity and a southward acceleration? Explain. Now, we've got vectors pointing in totally opposite directions. How does it even work? Well, this actually happens all the time in everyday life. Yes, anytime an object is moving north but is slowing down. Think about driving your car north towards a red light and you hit the brakes. Your velocity is still taking you north, you're physically moving that way, but your acceleration vector is pointing south, acting against your motion to reduce your speed. Acceleration pointing in the opposite direction of your velocity just means you're decelerating. Question 7, 8. As a freely falling object speeds up, what is happening to its acceleration? Does it increase, decrease, or stay the same? We know it's visibly falling faster and faster, right? So what does that mean for the acceleration?
Well, let's step through the motion. At position 1, the object has a low speed. By position 2, it has a higher speed, and at position 3, an even higher speed. The speed is absolutely going up. But, and this is super important, if we ignore air resistance, the acceleration stays exactly the same. Near Earth's surface, that acceleration is locked in at a constant 9.8 meters per second squared downward. The acceleration is just the rate that the speed is growing. The speed changes, sure, but the rate of change is totally fixed by gravity. Question 8 complete.
And now for our grand finale. Question 9. A ball is thrown upward with an initial speed of 5 meters per second. What will be its speed when it returns to its starting point?
This perfectly showcases the beautiful symmetry of freefall. If we ignore air resistance, the ball returns to its starting point with the exact same speed it left with, just in the opposite direction. On the way up, it leaves the hand at 5 meters per second. At its absolute highest point, as we saw earlier, its speed hits exactly 0. Then, as it falls back down, gravity accelerates it exactly as much as it decelerated it on the way up. So it crosses that starting line at exactly 5 meters per second downward. Initial speed equals final speed. Question 9 complete.
Understand the concept. Don't just memorize. That is the golden rule of physics, folks. We just ran through 9 specific situations, but these underlying laws, the difference between scalars and vectors, the constant pull of gravity, they are universal. The next time you toss your keys in the air or watch a car take a sharp turn, ask yourself, what invisible forces are dictating the movement of everything around you?